Hi everyone, this is Neha and welcome to the lecture on electronics troubleshooting. In this lecture, we're going to learn about measuring and testing of the capacitors and inductors, and also we'll learn about handling MOSFETs. So let's get started with capacitors. To measure the capacitor, we use capacitor meter, which is specifically designed to measure the capacitance value. And if you're using non-electric capacitor, then the polarity of the leads does not matter when connecting to the capacitor meter. But if you're using the electrolytic type capacitor, then you need to see the polarity of the leads. And you also need to make sure that you discharge the capacitor before you connect the leads of the capacitor to the capacitance meter. Last point, it is important to know that you are able to do the conversion from nanofarads to micro or picofarads, because these meters, they do not measure in nanofarads. So this basic conversion, you should be able to do it. Now next is leakage resistance of a capacitor. So this leakage resistance, it is a resistance which is in parallel with the capacitor, and that leakage resistance basically represents all leakage paths through which a capacitor can discharge. So actually the dielectric of the capacitor is never ideal or perfect. There will be some small current will be there between the terminals of the capacitor, and that will be either through the dielectric itself or through other insulating materials. So this small current is basically called your leakage current, and this is often represented by a resistance, by this parallel resistance with the capacitor when drawing its equivalent circuit, and that circuit we are going to see it in the next coming slides. So that resistance represents the leakage resistance. Okay. And let's see these points. There are three leakage paths of possible discharge. So these are the three leakage paths which are possible. The first is through the dielectric. So dielectric between in the capacitor present. Through that, it may be possible that the current can flow, and that is called your leakage current. Or through the or across the insulated case or body between the capacitor leads. So the leads of the capacitor, maybe through that you may have leakage current, and through the air surrounding the capacitors. So through the air also some leakage current can pass out. So these are the three possible cases of the discharge. And as a general rule, the larger the capacitor, then lower will be its leakage resistance. So by the formula of capacitance, you know that Xc is equals to 1 by 2 pi Fc. So here capacitor is inversely proportional to the Xc. So that's why we have inverse relationship between the leakage resistance and the capacitor. So lower the leakage resistance, you're going to have higher the capacitor value. Now going to the next topic, which is dielectric absorption. So dielectric absorption, it is the ability of a capacitor to completely discharge to zero. It is sometimes referred to as battery action or capacitor memory. So this dielectric absorption, which is also known as soakage and sometimes as dielectric hysteresis, is perhaps the least understood and potentially most damaging of various capacitors, parasitic effect. So what happens upon discharge? Most capacitors, they are reluctant to give up all of their charges, and due to this memory consequences, what happens if a capacitor is discharged by, let's say, by shorting, then open circuited again. So first it is shorted. So just imagine you have a capacitor and then you connect a short circuit, and all the charges will be discharged through that, and then again that short path is open circuited. Okay. Then what will happen? Then the voltage in the capacitor, it will start increasing from 0 towards the original value. So the capacitor, it exhibits a voltage memory because the dielectric molecules in the capacitor needs time to align themselves in an electric field. So that's your dielectric absorption. And let me draw one diagram so that you can better understand what I mean. Okay, so let's say this is your capacitor, and then you have some shortings. You have this wire going in here. So this is your capacitor, this is your shorting. So the capacitor will try to discharge through this wire, right? And then let's say right now it's short circuited, and later on you opened it up. Then what will happen? There will be some residual voltage inside this capacitor which will go up from 0 to some original value, right? So that's what is written here. Dielectric absorption is due to the dielectric effect. Where is this? Okay, so due to the dielectric of the capacitor retaining a charge after it is supposedly discharged, the effect of electric absorption is that it reduces the capacitance of the capacitor, which is obvious because some amount of charges will be dissipated through the shorting. So that will decrease the charges present in the capacitor, and thus the capacitive values will be reduced. All capacitors have at least some dielectric absorption. Dielectric absorption can be checked using a capacitor inductor analyzer. So all the capacitor, they have some amount of dielectric absorption, and that you can see on the data sheet as well. And you can use the capacitor inductor analyzer, which we also have in our lab, and you can use that to test the dielectric absorption. Now next is the equivalent circuit of resistances representing losses in the capacitor. So you can see this is the capacitor, and these are the three resistances which represent the loss in the capacitor. The first loss is due to plate and lead resistance. So the leads of the capacitor, due to these leads, so when there is a loss due to these leads, when there is a leakage current flows, that basically represented by this plate and lead resistance. And then you have this leakage resistance in the capacitor, represented by this RL. And then you have dielectric hysteresis losses. So this dielectric hysteresis loss basically occurs because in the dielectrics, it cannot instantaneously follow the cycle of continuous charge, discharge, and reverse charging that an applied AC voltage causes. And if the AC voltage is of higher frequency, then there may be a difference in the applied voltage and the actual voltage in the dielectric. So that the loss occurs at that time is basically is the result of the hysteresis present in the dielectric, and that loss increases with the increase in frequency. Now the second equivalent circuit which you see here, you see this ESR. It stands for equivalent series resistance, and this equivalent series resistance represents all losses of a capacitor. And this ESR is most often a problem in capacitors when used in high frequency filtering operations, for example, in computer power supplies. Now moving on to the next slide. Open or short-circuited capacitors are useless because they cannot store charge. So imagine if your capacitor is connected in a circuit, and if there is an open circuit, then that means capacitor will not be able to charge because there is an open before the capacitor is connected. And if there is a short, so let's say a lead is connected across the capacitor, then all the current will pass through the short circuit wire instead through the capacitor. The reason why, because the capacitor will offer more resistance compared to the short circuit wire. So that's why all the currents will pass through the short circuit wire, and in that situation also your capacitor will not be able to store the charge. Next is leaky capacitor is equivalent to a partial short circuit. Okay, so the leaky capacitor, that means some charges basically leaks out, some current leaks out in that capacitor. And if that happens, what does that mean? It means that the resistance in that capacitor is lower. Okay, so if the resistance is lower, then what will happen? Current will basically flow through that, because current tries to find a path of a lower resistance. So in that case, this capacitor, it loses its insulating properties, and gradually lowering its resistance. Now next is the type of capacitors and how their life changes, their values changes after over a period of time. So for electrolytic capacitor, it do not deteriorate with age while stored, because since there is no applied voltage. But if we talk about other capacitors, then they can change their values over time, but some are more prone to change than the others. So if we talk about the ceramic capacitor, then it can change the values from 10 to 15% during their first year. So this is important information, and if you want to learn this information about the capacitor, you need to see the data sheet and then check the value of the capacitor and how much its value has decreased when it was manufactured. So that information you can get through the data sheet. Now moving on to the next is checking capacitor using the ohm meter. So as you can see, this is the ohm meter, just an example connected to the capacitor. So when the ohm meter is initially connected, then its battery charges the capacitor. The battery of the ohm meter charges the capacitor, and the maximum current flows at the first instant of charge. Then the charging current decreases as the capacitor voltage increases towards the applied voltage, and therefore the needle, or if you are using this digital one, then the values basically slowly move towards the infinite resistance. And let's read here. The highest ohm range, such as 1 mega ohm, is preferable, because we want higher. If it has the high resistance, that means the capacitor is working correctly. Its dielectric doesn't have any leaks. Now let's read these 2 points. Disconnect one side of the capacitor from the circuit to eliminate any parallel resistance path that can lower the resistance. Keep fingers off the connection, since the body resistance lowers the reading. So this is important point when you are measuring the capacitor value. And then checking capacitor again with the ohm meter. So in this, for a good capacitor, the meter points moves quickly towards the low resistance side of the scale and then slowly recedes towards infinity. So as I said, the capacitor should show the high resistance, and that's what you will see when you connect it to the ohm meter. When the pointer stops moving, the reading is the dielectric resistance of the capacitor, which is normally very high. Electrolytic capacitor will usually measure a much lower resistance of about, so in case of electrolytic, you will get this resistance 500 kilo ohm to 10 mega ohm. And in all cases, you need to make sure that you discharge the capacitor before checking with the ohm meter. Now next topic is measuring and testing the inductors. So if you want to test the inductors, then you can use LCR meter, which is shown here on the right. This is a very handy equipment. Using this, you can easily measure the inductance. You can also use the DMM, but there are really few devices which will allow you to measure the value of the inductor. Most of them only measures the capacitors, resistors, so that stuff. So you can search online and see what are the different types of DMMs that allows you to measure the inductor. And the other device which you can use is the capacitor inductor analyzer, and this device is also there in the lab. So using this device you can measure the value of inductor, and another test instrument that is capable of measuring the inductor is the LCR meter, which I've shown you previously here. So this is the LCR meter. So it's the same thing written here. It's a handy equipment which can measure the inductor. So these so this is a really compact size of equipment of the meter. By using this you can measure inductor, and using this you can measure the capacitor also, inductor also, and dielectric absorption also you can basically measure using this meter. Now next in this we have this inductor which is connected to the ohm meter. So in case of inductor, this circuit, what it shows is that if there is the most common problem in the inductor is that there is a open wire inside the inductor itself. So you can see inductor is basically the coil. So this coil is open here, and if it is open, then what will happen? You will see the infinite value of resistance, because if there is any open, then there will be some air, and that air will offer infinite resistance. So an ohm meter connected across a coil reads infinite resistance for the open circuit. Now next is this equivalent resistance shown in the inductor, and this Ri basically represents the DC resistance, and this DC resistance equal to the resistance of the wire used in the winding. And it is important to know this resistance, because if the value of this resistance is normal, then that means your inductor is also normal, and if its value increases with a huge value, then you can assume that there's something is wrong with your inductor. So that's what it says here. Although resistance has no function in producing induced voltage, it is useful to know the DC coil resistance, because if it is normal, then the inductance can also be assumed to have its normal value. Now next topic is handling MOSFETs. So as you know, MOSFETs, they are very sensitive to electrostatic discharge due to their insulated gate source region, which is very very thin. So insulated this source region is made up of SiO2, silicon dioxide, and silicon dioxide is this layer, this insulating layer made up of silicon dioxide is very thin in the MOSFET, and we saw that in other classes when we learned about the MOSFET. So it's important to take precaution when using the MOSFET, and you know that MOSFET is a primary component in power conversion and switching circuits for appliances like your motor drivers and in switch mode power supplies. So for MOSFET, they boost a high input gate resistance while the current flowing through the channel between the source and the drain, which is controlled by the gate voltage. However, if you don't take precautions in handling the MOSFET, then it can basically lead to the damage of the MOSFET, and it can also cause and that damage can also be caused by over voltage. And if you exceed if you exceed the voltage and pass through the voltage across the MOSFET, then even in just few seconds your MOSFET will be destroyed. And so the typical failure mode for MOSFET is basically the short between source and the drain, and if you provide any higher voltage rating across that. So now next is never apply input signals when the DC power supply is off always wear a grounding strap on your wrist when you are handling the MOSFET, and then storing the MOSFET in a device in contact with the conducting foam. You have seen, like, most of the times when the equipments arrive from the manufacturer, they have a foam, so those leads are connected to the foams, and that basically protects the components. So in case of MOSFET also, you need to make sure that those leads you connect to the you basically you make sure that when you are storing the MOSFET, you connect with the conducting foam. So, and other than this, any high temperatures and operating condition outside the safe operating area can sabotage the MOSFET used in the switching circuits. So it is extremely important to observe these precautions to avoid possible damage to the MOSFET device. So that's all for today. Thank you so much for watching.